Hello, so let's continue. We just found a model for the sampling process. And this was important, this was in the previous video. Check it out. If we wanted to apply our continuous time Fourier transform to a signal that was sampled, to a discrete time signal, since the continuous time Fourier transform requires a signal at this continuous time, and for which we have a mathematical expression, we had to model the process of sampling in order to create that continuous time signal that was a sample signal. Now with that, we can derive the discrete time Fourier transform. And this is the ideal spectrum analyzer for discrete time signals. Now we're going to do it once as a derivation, starting with the continuous time Fourier transform. In the future, if you have a signal that is discrete time, you can just use this transform directly. This is indeed the mathematical ideal spectrum analyzer for signals that are discrete time and for which you have mathematical expression. So let's do it. Now, in order to derive it from the continuous time Fourier transform, we start with the continuous time Fourier transform, meaning the spectrum of the signal is the integral from minus infinity to infinity, x of t e to the minus j omega t dt equal. Now, remember, this is the continuous time Fourier transform. X of t is a function of continuous variable t, meaning t belongs to the set of real numbers, and we need to have a mathematical expression for it. Now, the signal was sampled, and what we found is that if the signal was sampled, we could model the sampling process by multiplying an impulse train, meaning impulses at the points at the sampling time instances times the signal. So we have a sum of x of nts times delta t minus nts, where we are using the sampling property of the impulse function from n equals minus infinity to infinity. And this, by the way, is our x of t sampled, which is x of t evaluated at t equals nts. Just check the previous video if you don't understand this step, why x of t of a sample signal can be modeled like this. And then this is times e to the minus j omega t dt. Okay. So all we have to do now is compute this integral, and we will find an expression for the spectrum of signals that were sampled, discrete time signals. Now, let's go ahead and check this. We are integrating with respect to dt. So I'm going to group the dt, the terms that have a t together, this one. And so this is equal to the summatory from n equals minus infinity to infinity, x of nts. Notice that nts is not a function of t. Here is nts, is a function of n. Notice that n indicates the order of the sample, it's an integer. And ts is the sampling period. So I take that out of the integral from minus infinity to infinity, delta t minus nts, that's our Dirac delta, e to the minus j omega t dt. And so all we have to do is to compute this integral here. And we are going to use the sampling property of the impulse function. Incidentally, we can derive just about all Fourier transforms that we need with really three things, three results. One of them, and I'm going to just put them here for a second, is the integral from minus infinity to infinity of e to the j omega t dt equals 2 pi delta omega. That's one of them. The other one is that the integral from minus infinity to infinity of delta t minus t0 times a function dt is equal to this. That's it. Now, you need to be able to integrate the exponential function, and that's it. Just being able to integrate the exponential function e to the ax dx equals, or at equals the exponential within the scaling factor, the exponential of e to the j omega t, and the sampling property of the delta. With that, you are able to derive all the Fourier transforms. And with previous results, you derive other results. So in this case, we are using the sampling property of the impulse function we have here. This also, by the way, works as long as you have t minus epsilon, t0 minus epsilon, t plus epsilon, as long as you capture the location of the impulse. That's exactly what we have here. This is equal to, I'm going to do it step by step, integral from minus infinity to infinity. That multiplication will be delta t minus nts times e to the minus j omega nts. This is the same now, which now it is not a function of t, so we are able to take it out. Right? And we are just left having to integrate the impulse. Take this out. And so what is the integral of an impulse? What is the area under the impulse? By definition, this is equal to 1. Right? And so what we have here is that the spectrum of a sample signal, you pick the samples, each one of the samples you multiply times e to the minus j omega nts, because it's a discrete set of samples. Instead of using an integral, that is what we use anytime that our independent variable is continuous, in this case it's a function of n, and that gives us the spectrum. We can define this as x of e to the j. I'm going to actually do it in the next step. So this is our expression for the spectrum for a sample signal. Now, in the signal, it contains information about time because you have here the nts. Now, remember that omega hat, the normalized radian frequency, is equal to 2 pi, the frequency, over the sampling frequency, right? And the sampling frequency is the inverse of the period. And so, if we wanted to write an expression that we will use for discrete time signals, for the spectrum, as a function of the discrete frequency, normalized frequency, this is just equal to the sum x of n e to the minus j omega hat. Notice that omega times ts here, so I'm going to give omega hat n from minus infinity to infinity. And this transform that you can use for a discrete time signal, for which a function n is an integer. So you have a discrete time signal, you multiply times e to the minus j omega hat, the radian frequency, and each one of these, just add them together, and you find the spectrum. This is known as the Discrete-Time Fourier Transform. Now, we derive it once. Would you need to do this every single time? No. You can just, from now on, if you have a continuous time signal for which you have a mathematical expression, you use the continuous time Fourier transform here. If you have a discrete continuous time Fourier transform, if you have a discrete time signal, you use for which you have a mathematical expression, or otherwise now you can also have the numbers, as long as you have the sequence of numbers, as well as this may be a finite set of numbers, 5, 7, 10, 12.1, minus 1. You will pick each number, multiply times the exponential, add that together, and that's the spectrum. Now, the same way that the continuous time Fourier transform is the ideal spectrum analyzer for continuous time signals, the discrete time Fourier transform is the ideal spectrum analyzer. It gives you the ideal spectrum for discrete time signals. Okay? Notice that we derive the discrete time Fourier transform using the continuous time Fourier transform for a sample signal. Now, look at the similarities also. In continuous time, so you have the signal, x of t, that's the continuous time signal. In discrete time, it's going to be x of n. You're going to multiply times e to the minus j omega t. In discrete time, it's going to be e to the minus j omega hat, the digital frequency, radio frequency, and instead of t is going to be n, our discrete time variable. In continuous time, because t belongs to R, you have an infinite number of points in between 2 points, you need to integrate from minus infinity to infinity with respect to that variable. In discrete time, you just add the discrete sum, because you have discrete values. That gives you the spectrum as a function of omega, which is a continuous variable. Discrete time Fourier transform gives us the spectrum as a function of the continuous digital frequency omega. Meaning this is something that you get an analytical expression. You can still not store it in a computer, you have an infinite amount of numbers. Right? It's omega here and omega here. In between 2 omegas, you have an infinite amount of omega. So in order to store it in the computer, we're going to need to evaluate this at some points to discretize it. And that's where we're going to go from the discrete time Fourier transform to the digital Fourier transform, that indeed the result is capable of being computed using a computer, a processor. A couple of other things that are important is that if we find the Fourier transform of the impulse train, you are also able to derive that there is a relationship, meaning the spectrum of the sample signal equals 1 over Ts, the sum of the original spectrum that you have, j omega minus k omega s, for k minus infinity to infinity. Let me just tell you what this means, and for that I'm going to need to minimize our result here. So we just derive that. Okay. If we have a continuous time signal, x of t, and we get a spectrum x of j omega, like this, for instance. This is x of j omega as a function of omega. if we sample x of t by evaluating it if we sample x of t by evaluating x of t at t equal nts, doing what I just did, what is the spectrum like of the sample? The spectrum is actually, this is the sample of the, I'm going to bring this up. This is what the spectrum is. So the spectrum of the sample signal is the original spectrum with the spectral replicas at the sampling frequency within a scaling factor of Ts. Let me explain that. The spectrum is going to be the same form, but you're going to have replicas centered at omega s minus omega s, and this keeps going, meaning at 2 omega s, you're going to get another one, 2, okay, or you can say that if you are doing this at omega hat, sorry, this is omega hat, you can say this is the sampling frequency, twice the sampling frequency, 3 times the sampling frequency, minus the sampling frequency, minus twice the sampling frequency, or in radians or in hertz, the same, or if you are doing it as a function of omega hat, which is 2 pi f over fs, then this is just 2 pi, minus 2 pi. This will be pi. And this amplitude is within a factor of Ts. So your spectrum that you had of your continuous signal, if you took samples, the spectrum you now computed with the discrete-time Fourier transform is going to be identical in form, multiplied times scaling factor that is 1 over Ts, and then you're going to have spectral replicas at omega s, 2 omega s, 3 omega s, 4 omega s, throughout, all the way to infinity, minus omega s, minus 2 omega s, all the way to infinity. This is the sampling frequency in radians, or the sampling frequency in hertz, or the normalized, this will be 2 pi. This also explains aliasing. If you do not sample fast enough, you will get, if this is fs, and fs is less than 2f max, you get the spectrum, spectral overlap, and this is aliasing. So what this equation is telling you here is that the spectrum from here to here has exactly the same form, but you have replicas. You could also express it as that the spectrum of the sample version of the signal is equal to, this is mathematical equality, is exactly equal to, within a scaling factor, 1 over Ts, that you multiply, the spectrum, I'm not going to put a sum, the original spectrum of the continuous signal, but for what? For this period. And this is what? Fs over 2. For omega equals absolute value, omega sampling over 2, or f, if we put it in the function of s, sampling fs over 2, or if you were to put it in the function of hat, for this absolute value 2 pi, meaning 2 pi over 2. They're saying that over here the spectrum that you have is identical to the original spectrum multiplied times Ts. Why is this important? Well, it's hugely important. It tells you that you can have a continuous time signal, you take the samples, and you can use the discrete time Fourier transform, and you are finding the spectrum. And what we're going to see in the next video is that we are going to go from the discrete time Fourier transform, again, it's still an ideal spectrum analyzer because this function here, this omega that we found before, this omega, is a continuous variable. There are an infinite number of points here. But if we evaluate the discrete time Fourier transform as a finite set of points, now that's computational. Now you can use any processor, any computer, to actually find the spectrum of any signal, whether you have a mathematical expression or not, as well as all the signals that you just recorded. Pick a signal, you do analog to digital conversion, so you sample it and you quantize it, and of all those signals, you can find the frequency content without having to do the Fourier integral, without even having to do this sum. And that's what we're going to see with the discrete Fourier transform, that is also known as the digital Fourier transform, which is our first transform capable of being computed by a processor, by a computer. Thank you.